So I'm just going to do a quick run through of doing a Psi-value calculation. This calculation I'm going to be running through today is an E6 junction, as you can see there on the screen. This is the PDF file that the client has supplied us with for this junction. It's a timber frame build-up, and yeah, as I say, it's an E6 junction, intermediate floor. Luckily, this drawing is fairly well labelled and got a decent amount of detail on there, which we can use to create an accurate model. Yeah, so don't need to be going backwards and forwards with the clients too much on this one. Yeah, so looking at the drawing, obviously it's in PDF format at the moment, and the first thing we're going to need to do is convert it into a CAD format, which would be a DWG or a DXF file. I use a website called easypdf.com for that, and I have already converted this one, so I'll just open up the DWG file. This is using LibreCAD, which is a free CAD software. Sometimes when you're converting files, funny things happen. Up here we've got the layer list, and we can see there's a big kind of white block there, which I know from experience is this H layer, so we'll remove that. And there we can see we've got now the polylines for the junction there. We'll delete out the unnecessary bits which aren't going to be included in the model. Let's make it nice and tidy. So that's basically our junction, and what we're going to do next is we're going to create, up here in the right hand corner we've got what you can see is the layers list, and what we want to end up with is a separate layer for each different type of material used in this build-up. So what I like to do first is kind of just add all the layers that I think I'm going to need, and I'm going to name them all as well. So for example, this is going to be plasterboard. I'll just name it P-board. This isn't going to be appearing on any reports or anything at this stage, so just name it quickly, something that you're going to just know for reference what it means. And for each layer, as you can see as well, I'm going to be assigning it a different color, just so they're all kind of definitive. This is going to be a softwood one. And then we've got 3 different insulations there. So I'm going to do ins 1. Quickly give that a color. And if you notice it, that's highlighted up there, ins 1. And if I click the plus sign now, it's automatically going to bring up insulation 2. So then you can quickly just go through those and get the 3 different ones added. So that's going to be a chipboard. And essentially, yeah, for each different material, we're going to add a different layer. I have already kind of progressed with this job, so I'll kind of just go through the basics of what you need to know and then skip forwards, I think. So once we've got all our layers in there, what we're then going to need to decide is how much of this are we going to include in the model? How much of this junction do we include in the model? And essentially that depends on the junction. So we'll start with what's called the flanking elements, which in this case it's going to be this section of wall here going up above the upper floor, and also this wall here going down below the upper floor. These are the flanking elements. They're heat loss elements, which basically they flank either side of the heat loss junction that we're modeling. And how we decide how much of that flanking element to include in the model is it essentially is the greater of 1 meter or 3 times the width of the flanking element. So basically, if this wall is under 333 millimeters wide, then it's going to be 1 meter long and then a meter below. But if it's more than that width, then it's going to be 3 times the width. Oh yeah, so we also need to scale this drawing, because when you've converted it from a PDF to a CAD file, the scaling might be out. So what we're going to do, I'll delete that, we don't need that. So we can lay down a polyline on an element which we know the dimension for. In this case, I know that this insulation in the wall is 100 mil thick. So we're just going to go across the thickness of that. And then if we highlight this line that I've just drawn there, we can see at the bottom the total length there is actually 9.983 mil, where it should be 100 mil. So to get the old calculator out, and we do 100, which is what we want it to be, divided by 9.983, and that gives us 9.983 divided by 100. 100 divided by 9.983. Oh yeah, okay, I don't know why that happened. So we've done the thickness 100 that we want divided by the thickness it currently is at, 9.983, and that's given us this result, 10 point blah 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 blah. So we're just going to copy that whole number there. We can delete, oh no, we'll leave it for now, that line, so we can check. Then we're going to select all of these lines and then come here and scale, click anywhere. We're going to select these X and Y coordinates here and just paste in that value that we've copied from the calculator. Hit OK and make sure it's deleting the original, so that we're just going to end up with the final size that we want. So we can click on this line again now, and hopefully we can see at the bottom there it's now 100 mil, which means that we've scaled it accurately. So yeah, going back to the flanking elements, what we're going to do is start drawing in the elements that we need to include in the model based on the layers that we've created here in our layers list. So the first thing I'm going to do is draw in the plasterboard, because the flanking element length starts at basically the internal corner point there, where the basically where the junction, where the wall ends and the junction begins, basically in the innermost corner. So for both parts of this, above and below the wall, we're going to start with the plasterboard because that's in the right spot there. And I'm going to hit the at key, and then we want to go up 1000 mil, and then it's the little back arrow key, and we choose the angle we want, which is 90 degrees, which is going to draw the line upwards. And that's kind of the final height we want then for that flanking element there. So then we can draw across, draw down and draw across again, and we've got kind of a complete circuit there for that material. When we transfer that over to the TRISCO software, that's going to kind of know that everything within that line is plasterboard. And it's basically a matter of kind of cracking on. Obviously with the softwood bits, we don't need to kind of go all the way up there, we just draw the timbers that are in here. we would draw around these timbers. We don't have to do them all separately either. If it's all the same material, we can kind of just include that in one polyline. And then obviously that cavity above it would go all the way up to the same height as we've just drawn the plasterboard. Yeah, and that's it really that's how you draw the lines in. Oh, the other decision we need to make here as well is how many of these studs, these not studs, sorry, these joists we want to include in this intermediate floor here. The way we do it in this case is we find out what the distance is between the studs, which I think is 400 in this case. Let's have a look. So we can measure it with a polyline here. Click on that. Yeah, it's 400 mil between the studs. So the rules state basically half of that distance, so 200 mil in this case, anything that's within 200 mil from this junction here, essentially from the corner, is going to be included in the model as a repeating bridge. In this case, it's the joists here. So even though we can see there's joist here and a joist here, when we're modeling it, we're actually going to only include this joist here, and then the rest of this intermediate floor is just going to be the insulation and the air gap above the insulation and the other materials obviously as well. So yeah, that's how we kind of make those decisions for this junction. Every junction has its own kind of set of rules, and also depending on the build up as well. If this was a steel frame junction, it would be quite different. We would have to kind of include any upright steel framework in the calculation, and then it would become a 3D calculation rather than a 2D calculation, which is what we're doing now. But yeah, I'm not going to kind of explain every single different junction or type of build-up that has its own set of rules, because we would be here all day, well, more than all day. So yeah, that's for this junction. This is kind of the strategy we're going with. So I'm just going to close this one. And open. So this is kind of what I've ended up with based on those rules. So we've gone a meter up, as I said, and a meter down from here. Also gone a meter back here and included only this joist and not included those two. You can actually turn on and off the viewing of the polylines up here. So if we hide that original polylines, we can see kind of what we're left with, which is the work that I've done on it. Yeah, it's not that obvious until you kind of switch between having it on and off exactly what goes where, but you can you just build it up as you go, and then you can turn it off to check if there's anything you've missed out or anything. But this one's complete now. So the next stage then is to import it into TRISCO, which, if I just close that, because that's what I'm working on now. So we can open an instance of TRISCO, and if we go into the corner up here, we've got the option to open a DXF, which we would have saved that from a DWG file. When we save it, it will turn into a DXF file, and it should be there wherever you saved it. So this is ours here. When you open it, it kind of gives you this box popping up here in case you wanted to exclude any of those polyline layers from your final model. And in this case, we do want to exclude that P layer there, which is the original lines that were on the drawing, because we've kind of gone over all of the ones we need to go over with all the different materials. So as you can see, we can just highlight ones we want to exclude. It's just that P1 we want to exclude from this, so we'll leave that highlighted, check there's nothing else in there we don't want, and then hit OK. And then it should import our polylines then. We can see our model there. So this is kind of the first stage of importing it into TRISCO. What we're doing at this stage now is kind of where we've created layers before in the CAD software, we've now got these layers down here. And they've got the same names we assigned them before, which is great for our reference. And what we need to do here is assign colors to them, basically, because each color in TRISCO is kind of what represents different materials. And there is a TRISCO file which has kind of all the colors listed in it for reference. I'll just drag it over here and show. So we can see the color number here on the left, and then in the middle we can see the name of the material that's associated with that color, and then on the right it shows us, you know, the thermal conductivity of each of those materials. So I'll just drag that over to my second screen so I can refer to it, and yeah, start entering in all the numbers here that we want basically for all these materials. And some of the materials are quite specific. For air gaps, which we'll go through in a minute, you kind of have to calculate the thermal conductivity. So there's not really an existing material you can assign for that. So I kind of just go with the lowest number that I know I'm not going to be using for any other materials, if that makes sense. Now for Psi-value calculations, what we're also concerned with is what are referred to as boundary conditions. So you might have noticed I've included a few lines in this model which actually weren't on the original drawing. So you can see here is the skirting board that was included in the drawing, but you can see around that I've drawn this kind of box here, which is going to represent a boundary condition. In this case, this is an internal boundary with a horizontal heat flow. Yeah, that's essentially all they are. The boundary conditions is there's different temperatures which different exposed surfaces are going to be at, and yeah, for the internal boundaries, you normally have a temperature of 20 degrees, and then we also do an external boundary condition, which is normally at 0 degrees, and then that kind of allows the software to kind of simulate the heat flow through that junction, which is obviously the whole purpose of figuring out how much heat is going to be lost. So yeah, that's why those are included there. And yeah, down in the bottom corner here, we can see I'm just going to wrap up these final numbers. So external boundary is 170, internal horizontal 174. And then internal up is going to be 182. You might have also noticed that I've actually missed out the boundary condition for internal with a downwards heat flow, which is going to go basically on top of this intermediate floor here. Little things like that, you know, if you forget to add it into a model or something, you can, if it's a simple enough structure, i.e. in this case it's just, you know, a rectangle block that I need to add into the model rather than something like this where there's angles on it. If it's just a rectangle, you can add it quite easily into TRISCO kind of afterwards rather than going back to the polylines and redoing it. So that's what I'm going to run through in a minute to show you how to do that. So once we've got all our colours assigned for the materials, then what we also can do here is kind of organize the materials by order of priority. And what that means is sometimes in a model you would have like materials kind of overlapping each other, and essentially it's just so the software knows which one you want to actually be taking priority in that space where there's two of them overlapping. I haven't actually done it here, but you could imagine if I'd drawn this boundary condition here, the internal horizontal boundary condition, if I had drawn that all the way around that skirting board like that, then I would want the skirting board to take priority, because otherwise, if this boundary condition was taking priority, then the skirting board would just kind of disappear behind the boundary condition. And we organize that by selecting the layers down here that we want to kind of organize, and then you've got two arrows up here. If you move it up, it has a lower priority. If you move it down, it has a higher priority. In this case, and I would recommend putting the work in during the CAD stage of it, so there's not too much stuff overlapping. So yeah, there's not too much priority for me to set, but just to show for an example here, I'm just going to move all the boundary conditions to the lowest kind of priority, as that's quite a common thing. Yeah, it's useful if you're doing like steel frame buildings where there's like quite intricate bits of steel work within the model, and you want to kind of have that within a layer of insulation. Sometimes rather than drawing the insulation or drawing that intricate bit of metal and then drawing intricately with the insulation around it, it's easier just to draw a block of insulation, draw the metal within it, and then prioritize the steel over the insulation. Yeah, so that's kind of all the colors in place, and then we're just going to set bitmap size and resolution. All we're checking here is pixel resolution needs to be 1. And then we're going to click on the magic wand icon up here, which is going to hopefully calculate a bitmap image. And we can see there for each different layer we've put in and modeled, it's quite nicely kind of assigned a color to it. You can kind of check it over, check you're happy. If there's anything you want to go back and change at the CAD stage, you can go back and change that, and then you'd have to kind of re-import it into TRISCO, and then sometimes it remembers the colors that you've put in for that particular model. Sometimes it doesn't. I don't really know why it forgets it sometimes, but assuming you're happy with it, what you're going to do then is actually just close it up here, and it's going to come up with a pop-up. Do you want to save the bitmap? We're going to say yes, and then it will probably save it under the same name that your CAD drawing was saved under, and in the same folder, which is ideal. You click save, and that's disappearing, and then you're kind of left with the original instance of TRISCO that you opened up, but now you've got this pop-up here. Do you want to convert bitmap into blocks? Use superposition of blocks? Yes. And then things to check here are, in this case, because it's a 2D model, or it's going to be a 2D calculation, I'm going to leave the object depth at 1 meter, and I will explain a bit more about that later. And down here, the grid unit is 0.01 meters. What we actually want it to be is 0.001 meters, so that the units are going to be in millimeters rather than centimeters. I'm going to hit OK, and then we can kind of do a little sense check. Is the model kind of the right size? Has it imported correctly in terms of scale as to how we want it to import? We sometimes get this big block around the model, which we have to delete out. So just a brief explanation about how TRISCO works, because we're in actually like the main part of TRISCO now, which is the 3D model. Even though I know this is a 2D model, but I'm modeling it in 3D, and then we're going to change it to a 2D model. It sounds like very complicated, but it is actually the simplest way I've found to do it anyway. So yeah, TRISCO, we have on the right side here, we've got the grid, because TRISCO, the way it's explained to me, is kind of a bit like a game of battleships where you've got a grid, you know, A1, A2, A3, B1, B2, B3, etc. Except in TRISCO, the grid is a 3D grid. So we've got the x-axis, y-axis, and a z-axis. And up here is kind of the information for the grid. So 0 to 1 on the x-axis refers to this space here, basically. 1 to 2 is kind of the next bit along, and then in order to get 1 point on that grid, you basically reference each of these axes and where on the axis you are kind of interested in looking at. And down here in the bottom left corner, we have blocks. So if we're going back to our kind of battleships analogy, we've got the grid, and then the blocks are what would be the battleships. So we're filling certain parts of the grid with blocks of certain materials. And because we've imported this, most of this should be kind of automatically filled out for you, which is great, because as you can imagine, kind of editing stuff like this can be quite complicated and time consuming. So you want to kind of get it as right as you can, put the work in during the CAD stage, and then that'll kind of save you time down the line, really. So yeah, each of these blocks is, you can see when you click on the block, it shows you on the main model which bit it's referring to. And you can see here it's got the grid references for which those blocks are occupying. So we can see this block number 2 here is the colours number 15, which is softwood, which is what we want. It's occupying the space between 24 and 25 on the x-axis. So if we refer back over here, we can see that is a width of 46 millimeters, and it's also occupying the space between 5 and 7 on the y-axis. So it's this, so we can see the numbers here, 5 to 6 on the y-axis is 100, and then 6 to 7 is 96. So we can see that total height of that block there is 196 mil. And then it's also occupying, of course, 0 to 1 on the z-axis, because that's the only the only grid we have for the z-axis is just 0 to 1, which is 1 meter, which is what we set earlier. Yeah, and then this kind of bottom middle bit here is the colors box, and that's where we kind of set the attributes for the colors that are included in the model. As I said earlier, some things are quite specific, and you need to kind of you have to manually calculate the values that are going to be entered, and then enter them manually as well down here. So let's first of all check that we're happy with the model. And we can see the materials here are kind of being displayed, but those boundary conditions, which I mentioned earlier, you can't really see them here, and that's because on this toolbar up here, it's selected to show materials. If we move along here, we can show boundary conditions. If I click that, it will show you we've got now all the materials have just gone kind of one color, and then the boundary conditions are all different colors. And we can see that we have got my horizontal boundaries here, So we can see we've got the horizontal internal boundaries here. Now we can actually like double click on them and select them as well if we want to. And then we can see we've got the internal boundary with an upwards direction of heat flow here. We can see there's no boundary for the internal with a downwards heat flow direction, which we mentioned earlier is missing from the model. And then that's our external boundary there, and they also appear down here as colours, obviously. And we can see kind of the values here. The exterior boundary condition there has a temperature of 0 degrees, and then indoors horizontal has 20 degrees. Little things like this also need to be checked because sometimes TRISCO kind of makes up its own mind about how it wants to work. So we're working to the standard of EN 6946, so we need to change that. And then we can check we've got the type is a boundary condition here, internal, horizontal, but we want that to be an upwards, so we can click that until it goes up. And that's kind of the right conditions for that boundary. So what we need to do then is we need to add in that internal downwards boundary condition, which I'll do. I'm not going to spend ages explaining how to do it, but I will do it fairly quickly and kind of give a brief explanation. So what we need to do is have a look at the grid first, and sometimes the easiest way to do that is to think about where we want to put this new material, this new color, or this new block, essentially is what it is. And we can select one kind of next to it. So we want to put one basically above this for the boundary condition. So we can select that block there. You can see down here, that's block number 22. And we can see its position within the grid. We're kind of mostly interested in the y-axis on this one because we want to go just above it. So we can see this block is in position 8 to 9 on the y-axis, which is a 20mm thick position here. So now I'm clicking on the grid up here. If I click above it, we can see that that's actually selected the grid below it. So confusingly, we would kind of want to click on the one below it, which gives us the one above it. And for the boundary conditions, we really only need them to be 1 millimeter thick. So what I'm going to do is split this part of the grid. So we see here, this is 9 to 10 on the y-axis, and it's currently 73 mil thick, but all I really need is 1 mil above that block there to put in my boundary condition. So I'm selecting this 73 mil thick section here, going up to grid up the top. We want to split it. Border 1, which is the border between the grid that I've selected and the one above it, and then we're going to split 1 millimeter off. So currently 73 mil. Once we've done this, there should be a new 1 mil section of the grid and then a 72 mil thick one underneath it, which we can see there. Now 9 to 10 is 1 mil thick, and 10 to 11 is the 72 mil thick, and we're still directly above that one there. So now we need to put in a new block for that boundary condition, and it's the same kind of hierarchy as before in terms of importance and overlapping other blocks. So with boundary conditions, I'm going to put it at the top. So what we do is I'm going to click on the top one that's already in the model, and up here we've got those two arrows which you remember from before, but this time instead of moving blocks around, they're for inserting blocks, and you can use them also to insert grid sections as well if you wanted to create a new grid section rather than splitting one out. So yeah, we're going to insert a new block above the top block there. So this new one I've inserted is essentially going to be the lowest priority one in the whole model because it's right at the top. Just refer to those colours again because we want an internal boundary condition with a downwards heat flow, which should be colour number 175. So I'm just typing that in the bottom there. So now that's given us colour 175. Let's check that. Yeah, so it's worth checking because as we can see here, this has given us a highly ventilated cavity, which is not what we wanted. We wanted an internal, unventilated, downwards heat flow boundary condition. So we're just going to delete that wording out of there. Internal down. Then we can set the temperature to 20. All the rest of that is correctly set up. So now we just need to put that boundary in its proper place. So we remember where we've created that new grid section for the boundary condition on the y-axis. It's 9 to 10, and that's that 1 mil section there. So what we're going to do down here is just put 9 to 10 there, and that's given it the correct height. Z-axis is always going to be 0 to 1 in this 2D model. And then the x-axis, we basically want to go above this block, but in front of that skirting board. Not that it matters because any overlapping materials are going to supersede that boundary condition, but just to show you how to kind of enter it in if you needed to enter it in more precisely. So we've selected this one, and now we're looking at the x-axis, which is 8 to 26. So we can enter that in, 8 to 26, which gets us roughly in the right place. You can see now there, but we want to go in front of that skirting board. So what I'll do is select that skirting board. And we can see that that is 11 to 22. So I'm thinking this last bit here, which we actually want to occupy, is going to be 22 to 26. There, which puts us exactly where we want to be with that. So we can click on boundary conditions again now, and as we can see, that has successfully put that boundary condition in the right place there where it needs to be. And then we're happy with the boundary conditions, we're happy with the placement of materials. So now it is a case of going through this bottom middle section here and making sure all the materials they have the right attributes that we want to give them. So for example, where, as I was earlier entering in kind of random numbers for the materials which we needed to adjust, you can see that should be an air cavity there, but because I've just given it a random number, it's actually aluminium at the moment with a thermal conductivity of 160, which is obviously like way too much. So what we're going to do is rename that, and then we are going to calculate the airspace, which is going to go in there, and we're going to calculate the conductivity of that, and we have an Excel sheet to help us with that. This is kind of the master Excel sheet for Psi-value calculations. You get given this when you attend the Elmhurst Psi-value training course. So this is the main sheet. What we're doing at the moment is calculating airspace resistance. So we're going to click on this tab at the bottom here, airspace R. I won't go into too much detail because a lot of this is kind of out of the scope of this video. A lot of this information you need to kind of go and learn from the Elmhurst on the 4-day training course, because there's just so much that goes with it. But essentially this air cavity needs to be calculated in a special way because of its position and the size. of it. So the way we calculate this kind of cavity is we're going to get the height of it, which we can do by looking at the y-axis. We've got that selected already, so the y-axis is 6 to 7, so it's 96 mil high. And then we go back to our spreadsheet, and the heat flow direction is going to be horizontal. So the height is going to be the B value. D is the direction of heat flow, and B is kind of the other direction, or the direction across the heat flow, should I say. So what was that, 96? And in this case, because it's a special case, we're going to double that, which gives us 192, which is the value we'll use for D. As I say, I'm not going to really go into details of why that is, because that's very complicated and beyond the scope of this video, really. But once we've entered the values here, it's going to give us the thermal conductivity of that airspace, which is 0.7772. So we can go back to TRISCO and change that from 160 to 0.7772, which is the right value for that airspace. And yeah, at this stage, it's essentially going through all of these materials and making sure they've got the correct values, which represent the actual wall, the model. So I'm just going to go through and do that now quickly. So I've gone through all my list of colours now, and got them all set up how they should be. All the conductivities are correct now, and I've renamed them all to kind of represent the materials. So the next stage now is to go to grid up here. It's currently at the minimum grid, which means that it's just set to have the minimum required grid to fit in the blocks that are in the model. But when we're actually going to run the simulation, what we need to do is have more grid spaces than that, because the simulation is going to kind of measure the heat or the temperature at each grid reference point. So in order to kind of get an accurate result from that and kind of factor in the heat transfer more accurately, it's good to kind of break down the grid into smaller pieces. So to do that, we just go to auto split up here. Default settings should be all good. Hit OK, and now we can see that that grid's been split into a lot of smaller pieces, particularly where there's materials in the grid. And yeah, that's it. Boundary conditions all in place, materials all set up, and now it's time to run the simulation, which shouldn't take too long, seeing as this is a 2D model. It's a matter of seconds there. So yeah, we can see there, after a few seconds, the temperature distribution has kind of appeared, which means that the simulation is complete. Now it's very pretty and everything, but we need to kind of go and get the tangible results. In order to do that, we'll go first edit and then derive the thermal properties here. And then I normally just tick all these boxes. You can give it a name, E6. And now that we've ticked all those boxes, we can click on the report up here, text output, and then that gives us all these values. The one we're mostly interested in is Q up here, equal to 7.551 watts. That is the heat loss for the whole model, given obviously the internal boundary conditions and the external boundary conditions. That's all the heat that's flowing from between those boundary conditions, basically. Also down here we can see the minimum temperature within those boundary conditions. So for the boundary condition internal down and indoors reduced, that's the minimum temperatures at those boundaries, which we use to kind of get the risk of condensation. So now we're going to look at taking this data we've got from this output and converting that into a psi value. So I'm just going to open up the Excel sheet for the psi values again. Again, very briefly, I'm just going to go over what I'm going to do in this instance, but obviously there's a lot of different types of junction, a lot of different ways to do it. As I mentioned before, this is a 2D calculation we're going to do. Obviously, I've done a 3D model, so this is kind of where we're going to convert that 3D model into a 2D calculation. So looking up here at the spreadsheet, we've got the option to select 2D or 3D. We're going to choose 2D, and we've got the option for the heat loss value here. Now we have got the option to put in the Q value, which is the output from the model. I normally always do the L2D value for a 2D calculation, and let's do the Q value for a 3D calculation. So in this case, we choose L2D, then we just need to convert that Q value into an L2D value. So in order to do that, the difference between them is a Q is heat loss for the whole model, which is a 3D model, and L2D is like a linear value of heat loss. So that would be like, in the case of this 3D model, let's just have a look. L2D value would be kind of from a point here in a linear fashion, kind of along the z-axis, would be kind of that value rather than for the whole model. So it's fairly easy to convert one to the other. So going back to the text output, we've got our Q value here for the whole model, 7.551. To convert that to an L2D value, all we need to do is, first of all, we divide it by the width of the model in meters. This is why we set it to 1 meter earlier, because we divide it by 1, it's exactly the same value. Obviously, if it was 600 mil wide, then you'd have to divide it by 0.6, and then it would be kind of a different value. But when I'm doing it this way, I always try and make the width of it 1 meter, just to simplify this part of it. So Q is 7.551, still 7.551, even when we've divided it by the width of the model. So then all we need to do is take that value, 0.551, and we divide it by the difference in temperature between the internal and external boundary conditions, which is 20 degrees, seeing as the outside temperature is 0 and the inside temperature is 20. So we divide that by 20, and there it is, that's our LTD value there, 0.37755. So we are just going to enter that into the spreadsheet, 0.37755. So that's the LTD value, and then the next stage is, that's heat loss for the whole model, but we kind of want to, we just want heat loss for that junction, don't we? We don't want to incorporate the heat loss that's from these walls or any other flanking element, because that's kind of already accounted for within the U values of those building elements. But because we've set it to a certain length, as we set it to 1 meter earlier, didn't we, for each flanking element, what we can do is subtract the heat loss from those flanking elements from the overall model, and then what we're left with then is just the heat loss from the junction, which is, that's essentially what the psi value is. Luckily the spreadsheet does most of the hard work of that for us. So we've got, here is where we enter the length of the flanking element. As you can see up here, flanking element 1 is set to calculated, and on this spreadsheet that means that there's, when you set it to calculated, I'll do it for flanking element 2 here because that's manual at the moment. This is for a different junction. So if I set that to calculated, now we look at the bottom, we can see that flanking element 2 has appeared down here. So these tabs are essentially, they're just U-value calculators where you can enter all the materials, thicknesses, thermal conductivity, and then that automatically puts the U-value back into this main part of the spreadsheet. So we can see here where it's got U for flanking element 1, that's the output of that other page on the spreadsheet, which that's actually already set up correctly for that wall. And because both flanking elements in this case are exactly the same wall, what I'm actually going to do is change that back to manual. Just for clarity, I'll change that to wall there. So instead of that being automatically calculated now, that U value, I'm just going to manually put that U value in for flanking element 2 as well. 722. And then we're going to set the length of flanking element 2 as well. So flanking element 1 would be the wall, above the intermediate floor. Flanking element 2, same wall below. So we're removing 2 meters of that wall essentially from the model. And then whatever's left over is the psi value, which is kind of spat out down here. So yeah, it's fairly straightforward. And then for the condensation risk analysis, we can go back to the TRISCO output data, look at these boundary conditions for the internal boundary conditions. So we're not looking at the exterior here, we're looking at these 3. We're going to pick the lowest temperature here out of these minimum temperatures, because the point at which is the lowest temperature is going to be the most at risk of condensation. So in this instance it's 19.3712. So we go back to our spreadsheet, we can manually enter that here. 19.3712 was it? 3712, yeah. Manually enter that into there, and then it gives us that value there, that's essentially just a factor of dividing the internal temperature by the lowest temperature on the internal surface as calculated by the model. Any value below 75 indicates a risk of condensation, and any value above indicates no risk of condensation. So we're at 0.97 here, which is really great. So yeah, that's pretty much the calculation side of things done, and then it's just a matter of popping it into a certificate, which is fairly straightforward. Kind of use a template for this normally. So here's the template spreadsheet, which has obviously got information in it already from the last one I've done, so we can just kind of quickly adapt that to suit the current one, which is E6 intermediate floor. I'll change that in a minute. Yeah, we put in a few kind of details about the general construction specification, just so that anybody looking at the certificate can't just kind of apply it to any build up. It kind of needs to be specific to this build up, which is why I obviously include the thickness of the insulation and the thermal conductivity. So I'm going to remove any bits that are specific to that sill junction that was previously in there, and then we can kind of find some specific information about this junction. So perhaps we would like to put in the depth of this mineral wall here, which means we're going to minimize the grid again, and the height 4 to 5. It's 100 mil. So I just put 100 mil mineral wall in intermediate floor. and we'll put in the conductivity value for that as well. Yep, and then get rid of these pictures because they're obviously not relevant to this junction. We get this imagery. First of all, I'll get the temperature distribution one, which comes from the actual model. I'll just have to run this calculation again because we've refined that grid. So clicking this graphic output button up here gives it kind of more of a blocky feel, and then we can kind of get square, looking square over the junction like this with these buttons here. It kind of gives it different angles, viewing angles. And then this button here will kind of overlay the temperature distribution, so we can see kind of the outlines of the materials, temperature distribution. It's all like looking directly down onto it. So just take a screenshot of that. And just paste that in at the right size. Now we could use the original drawing provided to us by the client for the other side where it says detail. I prefer if we get the polylines because we've kind of tidied these up already. So what I'll do is, if we click here, that will kind of hide all layers, and then we'll just view the original P layer there, which kind of gives us a nice visual detail. And then if we go to print preview, it should kind of give us black lines on a white background rather than the other way around, which looks good on the certificate. And then we can just kind of get a snippet of that, where the area of interest is, and then kind of paste that in the other side. Try and make them match a little bit so that it kind of makes it easy for people to compare the two and see what is what. And then it's just a matter of putting in the values that we've got here. That's still set to ground floor there, but that doesn't really make a difference to the output. So the Psi-value is 0.0331. So it's just literally just a matter of typing that in, 0.0331. The temperature factor was 98, was it? 0.97. Which is good. And then just pop today's date in here. Certificate number. Just put in the relevant code really, for depending on what junction it is. I can't remember what code I've chosen for the intermediate floor junction, so I'll just refer to that. So yeah, I've got a spreadsheet which I keep track of all the ones I've done. So here's the code for it. That's a previous one, so this is going to be number 2, which the code is just ATSPACE, and then external EWIF stands for external wall intermediate floor, and then the number's just the number of junctions we've done of that type essentially, and we just use that as the reference for the certificate, and then that's it, job done.